Okay, hello everybody. Welcome to the second class of AS A levels 9608. So we will going to complete the topics regarding the number system conversions, and we will going to cover the two's complement as well. Just give me a minute, so I just get in touch with my students. They may be waiting. Okay, these lectures will be launched on air as well on YouTube, so you people can watch it later on. So I'm just sharing this link with my students on Facebook and on WhatsApp. Okay, so um, we just started. So I can see Mufaru is with us. He's from Zimbabwe. I have two students from Zimbabwe, one student from Zambia, and one from Tanzania. And definitely all the students out there on Facebook, they are also with us, and students on YouTube as well. So just like last time, I will going to share my screen, my desktop screen with you. I'm using Ubuntu 14.04, the operating system, and then I will going to use my smartphone screen as well, which I will going to use as my whiteboard, e-whiteboard, which I used to call it. So just before moving into that number system that we have done in the previous class, we done binary to decimal conversion, and then decimal to binary conversion, and then from binary to hexadecimal number systems, and from hexadecimal number systems to binary again. So we will going to do a little practice first. So get in touch with me. I will also going to share the link with you, so you can get the worksheet, the notes from there as well. So this is the page, Wikibooks. They have done it pretty good. So I will be sharing this whole link right now on my Facebook page, so you can get here at A level computer science. You can search it on Facebook. The banner looks like this. Oh, sorry, I haven't shared the screen, so just wait for a while. Okay, here we go. Here we go. Okay, so this is the A level computer science page, and this is the panel looks like. So just get added here. I have a request here. Right, so I'm going to add you like this. I'm sharing the link. This is the number system conversions, not only the notes but as well as the worksheets, examples that you are going to cover. Okay. AS structure to notes or number system conversions. There we go. Just get it from here and start solving them with me. I'll definitely going to help you out. And if you are going to done with this, we will be done with the number system conversions. Okay, there we go. So let me open the same link on my note. There we go. the reason of opening this on my node is that so I can edit it live and share it with you people. Okay, there we are. Okay. So the fundamentals of data representation, a binary number system is the very first topic that we were going to start. We have actually done it in the previous lecture. This is a table that will going to come again and again. The hexadecimal, the binary, and the generic. So that's, for example, here that is the hexadecimal number. This is the binary equivalent, definitely 0. It is represented as 0000. Definitely it can be represented as 1 bit in binary as well, but the reason of starting this 4 bits, all these 4 bits here, is because this table will going to comprise of total all the 16 digits of hexadecimal number up to F. Basically up to F, it's completed. They from 0 to F are the numbers that we have in hexadecimal. Then in binary we have only 2 numbers, 0 and 1. But and in decimal number system, how many numbers do we have? We have from 0 to 9. It makes total 10 numbers. So this is the reason we call that decimal number. So this F is equal to what? In decimal, it is equal to 15. And what is it equal to? This 15 and this F is equal to what? What is equal to in binary? It is equal to 1, 1, 1, and 1. So we have done already the conversion. So that's pretty easy. Okay. So the ternary number system, as they have already mentioned, from 0 to 9, we have done it. Forget about this thing and this thing as well. So this is the binary number system. It has only 2 numbers, 0 and 1. So 0 and 1 are the 2 numbers in binary number system. And then we have, this is the example that we have done already, how to convert numbers like 1, 1, 0, 1, 0, 1, 1. Just like this 1, 2, 4, 8, 16, 32, 64. We have practiced this pattern already, so you can get it from here as well. Now, why this the very first bit is equal to 1 is because 2 raised to power 0. So the formula that we need to remember is 2 raised to power n. And just give me a second. So let me check on my screen that if he is having some troubles. Okay. So Miraj is texting me. Maybe he just okay. All right. So here we are. So we have done this in the previous lecture. You can watch the video on the Facebook. Also, the same thing I've covered in the O levels and number system conversions in the very first introduction class. You can get help from there as well. So there we are. Now we need to do exercise. As we will going to do the exercise, we will going to get the idea. Convert the following binary numbers into ternary. So solve with me. Let's see who can solve it first. You and me. All right. So how many bits we have? We have 1, 2, 3, 4, 5, 6, 7, and 8 bits. So just I'm going to rewrite the number here. 0, 0, 0, 0, 1, 1, and 0, 0. So this is a number. I've just simply rewritten it. This 2 means basically base 2. So just to make sure that this is a binary number, this whole number is a binary number. So I've rewritten the whole number, and I'm going to convert it into decimal. It's into its decimal equivalent. So let's start giving it power. The pattern that we have already remembered: 1, 2, 4, 8, 16, 32, 64, and 128. So if it's not just clear, let me just do it again. I can write the numbers in the bottom as well. I can make the boxes as well, something like this. Okay, so this is just take a little longer. Okay, the first zero, it's 1, it's 2, it's not 3, it's 4, it's 8 because we're calling the power to raised to power n. This is 16, this is 32, this is 64, and this is 128. The 8th bit is the 128. So these all are zeros, so no concern. They are doing no addition. This 8 has 1, so we're gonna take this 8. This 4 has 1, so we're going to take this 4. And then we have the zeros, so just leave them as it is. So 8 plus 4 is equal to what? It's is equal to 12. So 12 is the decimal equivalent of this whole number. All right, so let's check. All right, 12 is the decimal equivalent of this whole number. So they have done it in the same pattern that we have done already. So this is how we can convert all the binary numbers into decimal and vice versa. These are some other practice questions that you can do later on all by yourself from your home. And if you have any problem, you can share your problem with me on the Facebook page. I'm going to answer you there. All right. So what if we have a decimal number? Can we do one more example? I guess let's move on with it. It's pretty easy. Max and range. So this is a good thing. This is a thing that they will going to ask you questions about this thing. For example, if they will going to give you a register, for example, this is a register and it's a 1, 2, 3, and 4 bit long, right? 1, 2, 3, and 4 bit long. So they will going to ask you that what is the maximum number, what is the maximum value that you can store into this register? Can you answer this question? It's pretty simple. If all the bits of this register is high mean 1, it will going to give us the maximum value 1, 1, 1, and 1. This 4-bit register has all the values high, all the values 1. It will going to give us the maximum number. How's that? For example, just simply convert the value of this register. We already know the pattern. That is 1, 2, 4, and 8. All the values are 1. So 8 plus 4 plus 2 plus 1 will going to give us 15. So 15 is the maximum value that it will going to give us if this 4-bit register, this is a 4-bit register and it can give us the maximum value 15. All right. So what could be the minimum value? Definitely 0 will be the minimum value if all the bits are 0. So this is the max thing. Okay. Definitely they are just giving this formula as well. But this formula should not confuse you because the method that I have just told you already, that will going to work fine. That's enough. 2 raised to power n minus 1, nothing basically. For example, if we have a 3-bit register, if all the values, what is the maximum number this register can store? So simply put the ones and convert the number. That is 1, 2, 4. And 4 plus 2 plus 1, it will going to give us what? 7. All right. So basically what that is trying to say is that How many bits this register has? This register has 3 bits. All right. So what you will going to do? 2 raised to power n. So how many bits? We have 3 bits. So put the power 3 here and use this formula -1. What is 2 raised to power 3? 2 raised to power 3 is 8. So 8 minus 12 going to give you 7. So both the methods are fine, but I just find this method more practical, helping, less confusing. So I taught my students this first, and then I just told them, okay, go with the formula as well. That's up to you. But you just have to memorize this whole thing. That is really important. Max and range of binary numbers. We have done it. The thing that we have already done. Some practice questions. Now the hexadecimal number system. Hexadecimal number has how many values? It has how many numbers? It has from 0 to F. It has 16 numbers. Right. Sorry for this messages and all those things. Just keep disturbing us. You can disturb me during the lecture as well. I will definitely going to reply you. That is definitely not the student. That could be my Facebook friend. So there is basically the motivation behind the using of hexadecimal number system. You can see that this is a pretty long decimal number, and when you will going to represent this long number into binary, it will get even longer length. But when you will going to represent the same lengthy number in hexadecimal, it's sufficient, and it will going to have less number of digits. So when we need to represent very large numbers in computers, we use hexadecimal number system. Okay. So convert the following hex numbers into decimal numbers. When you are going to do, look, we have done the binary to hexa, hexa to binary, binary to decimal, and decimal to binary conversions. How we will going to convert decimal to hexadecimal? The simple thing is that even though there are direct methods, but if you have one simple solution, I'll prefer that you just stick to that. The reason is that it's simple. So if they are going to tell you that there is a number, for example, BF, this is not the abbreviation of something. This is a hexadecimal number. So if you need to convert this number into its decimal equivalent, how you are going to do that? What is the method? It's pretty easy. You know the conversion from hexa to binary. So simply convert this number into its binary equivalent. And once you have found the binary equivalent, then later on you can convert, because you know hexadecimal to binary conversion, and you also know from binary to decimal conversion. So you can use this two-step method, and after converting that binary number, you can later on convert that binary number into decimal, and this is how you are going to get your answer. It's pretty easy. Just let's do this quickly. This is going to give us a quick revision. Okay. How we will going to convert this number into binary? It's pretty easy. What this b is equal to? It's b is equal to a is equal to 10. You can look into the table above, and b is equal to 11 in decimal, and this f is equal to 15 in decimal. Don't get confused. This 1115 1115 is not the answer. This is, for example, some student may make the mistake that they will going to go, okay, we have converted the number, this is the answer. No, this is not the answer. This is not the decimal equivalent of the binary number, this hexadecimal number system. So be careful. Okay. So 11 and 15. Now, how to represent this 11 in binary? Just remember the pattern: 1, 2, 4, 8. 1, 2, 4, and 8. So we need to make 11. 1. This will make 12. Okay, leave it. 8 and 2, 10, and then this is 11. Now to represent 11, we need to 8 plus 4, 12 plus 2, 14 plus 1, 15. So this is the binary equivalent of the number that is given above. So we have done with the binary conversion. Now convert this binary number into what? Into its decimal equivalent. That's easy. Simply rewrite the number, that is 1 0 1 1 1 1 and 1 1. Now we're converting a binary number into its decimal equivalent. So 1 2 4 8. We are not going to repeat 1 2 4 8 because we're converting from binary to decimal. So it will become 16. It will become 32. It will become 64, and it will become 128. So 128 is on. My bad, we have less space. And we are also not using the whiteboard. So let's do it here. Okay. So 128 will add up. This will not going to add up into 32 and 16 and 8 and 4 and 2 and 1. Can somebody pass me the calculator? Nobody will going to do that. So I'll have to add these all values by myself. 128, 128. Just give me a second, just to make sure we can use the calculator. All right. I do have a Windows 10, and this laptop is the same laptop, and on my PC on my gaming rig, but I just prefer Ubuntu. It's flexible for the programmers and the persons who really love computer. Windows is just for the novice people, honestly, but it does have its problems. So 128 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1. What is the answer? 191 is the answer. So if we have this question BF here, what will be the answer? The answer will be 191. This is the decimal equivalent of this number. Just go Google and find it. What is this BF is equal to? It's pretty simple. So, all right. This is how you're going to do that. Converting between bases. We have done it already. Oh, it's a pretty long number. They will not going to give you a number more larger than 8 bits. So this is just for practice, but you can leave it as well. So this is a two-step method. They're just giving you that if F5F is the number, that is the hexadecimal number, you need to convert it to decimal. You first convert it into binary, and then you convert binary number to decimal. So you can convert it like this. So these are all the practice questions that you are going to do. Let me know if that you cannot do that. This is very important. So this is all about the number system conversions from prime binary to decimal, decimal to binary, hexadecimal to binary, and binary to hexadecimal, and from decimal to hexa and hexa to decimal. Let us move on with the next topic, that is 2's complement. This is a new topic that is given in AS, because so far the thing that we have done is also being done in O levels as well, in O level computer science. So we have done here with this whole thing. Just let me know if there are any problems. And just given the questions here. Okay. So here on this page. Okay, Mufaru want to join the group as well. That's good. Mufaru, do let me know that. Yeah. If you have any questions, I'm just Tagging you here as well. There you go. Okay. So let's move on with the next thing, that is 2's complement. There we go. 2's complement. Just let me have a look that everything is going fine. Yeah, everything is going fine. All right. So the 2's complement. Now, what is this 2's complement is? Just let me take this whole slide into my note so I can just later on add the description by myself. Or just we can use a note. Okay. So look here. This is a number 0101. They are saying that this is a positive number. What if you need to represent a -5 in computer? How you can represent -5? So there is a method of doing that, because computer only can store numbers in form of zeros and ones. It cannot store something like minus and positive and multiply and divide. So we need to tell it. We need to code it so computer can understand that. Okay, if you give me this number, if you have this pattern, it's mean this is a -5. So there is a hard and fast universal rule that if you need to convert any positive number, you have to take 2's complement to make the same number into negative. For example, if I ask you to represent a -37, you will going to do it in the same way. So what this 2's complement is, that's pretty easy. If you have given a number, for example, this 01 and 01 here, 2's complement. Okay, just let me share the very same slide with you people. So if you want to look at your side on your PCs or smartphone or laptops, etc., you can get that as well. So I'm just sharing it live on the page. There you go. Let's choose complement. Available on the page. So you can simply comment here if you need to ask any questions. All right. So 2's complement. The number is 0101. So this is a number 01. And what we need to do, we need to represent -5. All right. So how to do that? If you simply convert this number into decimal, now you know pretty much 1, 2, 4, and 8. And this will going to cut because it's 0. This will going to cut as well because this is 0 as well. So 4 plus 1 is equal to 5. So this number is right now representing +5. So now we also have to take care of the sign as well. So far we are all using the unsigned numbers. All right. So how to convert this number into its into minus number? First, you will going to take 1's complement. What is 1's complement? You simply take this number and you inverse it. You simply take the number, whatever the number that you need to take 2's complement. First, you are going to do what? You need to take 1's complement. And what is 1's complement? You simply reverse the whole numbers. For example, the first 0, you will going to write it 1. This is 1, you will going to write it 0. Now this is 0, you will going to write down 1. And this is 1, you will going to write it 0. So this number has become now 1010. This is the 1's complement. This is the 1's complement of this number. We are done with that? Okay. So now we have taken the 1's complement. What is 2's complement? Simply add 1 at the last. Simply add 1. So how we will going to add the 2's complement? We're adding 1. Okay. So in binary, there are some rules of adding the numbers. We will going to practice some one or two more questions, so you will going to have more idea. This, there is a 0, so there is a 1. So what we are going to write down? We will write down 1. So this will come. This will come down here like this. 0 and 1. This number is representing what? It's representing -5. Okay, this number is equal to -5. All the numbers having value that comes with the minus sign, they will always going to have the leftmost bit as 1. So this is one example. If you will going to look into, if they will going to mention that this is a signed number, they will going to use signed. Okay, so if they're saying that the numbers are signed, and if you look into any number and you find out that the very first leftmost bit is 0, so what you will going to say, this is a negative number. So if they are going to say unsigned, so it doesn't really matter that it starts with 1 or 0. It will always going to give you a number into a positive number. But if they are saying that the computer is using a signed numbers and the very leftmost bit is 1, so it's confirmed that this number is a negative number. So now you are going to represent this number as a negative number. All right. So the 2's complement. Let's solve another example. Let's see some other questions from the notes. These notes are basically state provided you by the CIE, the helping notes. These all notes are definitely are part of syllabus. So there is nothing that I'm just making something out of myself and just Google some information and just passing it to you. These links are provided by the CIE itself here. So I'm just taking help from my teacher's scheme of work. So that's pretty good. That's pretty helpful. You can even have just uploaded this teacher's scheme of work on the A-level site as well, which I've told in the very first class. This is the site. There you go. So you can also get the scheme of work from there as well. That is under the syllabus. There it is. So you can get help from there as well. But as if you basically, this is not encouraged by CIE or even me to the students, because if you will going to look into it all by yourself, that's okay if you want to. This is the reason that I've just put it here, so it's available. But if you will going to look it all by yourself, you might get confused. So definitely, just like you need a senpai, you need a sensei, you need a teacher. So this is the reason I'm here to guide you people. I love to guide. I love teaching. I love my students. Okay. So these all are examples. They love making tables. So there is another table for the reference, the positive number, and the -7 is represented like this. All right. So let's do another example in which if we need to add up something like this, what's going to happen? Okay. Let's do one more example. So how a +6 can be represented? you can do it yourself into binary. 1 2 4 8 0 1 1 0. This will going to represent positive 6. 4 plus 2. Okay, so 0 1 1 0 is positive 6. We need to represent what? Minus 6. So takes 1's complement. What is 1's complement? Simply reverse the numbers. 1 0 0 1. And what is 2's complement? Add the 1. So the reason of bringing this question here is that now you're going to add 1 here. What happens in the binary if the value is 1 1? 1 and 1 is equal to what? It is equal to 1 0. Now what is 1 0 is basically? Or you can also say that what happens in decimal number system if you add two numbers and you have to take carry. If two numbers, for example, you have to add 7 and 6, and add 7 and 6 we're going to do what? For example, if this is a number and you need to add 6 here, what will happen? 6 and 7 is equal to what? This is equal to 11. Or it is equal to 13. It is equal to 13. So you will going to take 3 here and you will going to carry 1 here. So the same method will going to be used here in this binary number is because in binary number system there is no number greater than 1. There is only 0 and 1. So if there are two 1s, we will going to put 0 here, alright, and we will going to carry 1 here. So this 1 will be carried, and what will be the answer now? This will become 0 1 0 and 1. So this is the minus 6. Let's check it in the table as well. 1 0 1 0 1 0 1 0. So this is your minus 6. Okay, so this is how you will going to add up numbers. You will going to take care of this this thing that I've just told you, this carry stuff. Put 0 here and you carry 1. Okay, so do remember that this happens when we have two 1s. That's good. Ask me if you need to revise this particular thing, because sometime you will going to have problem with this. No, everybody is good with that. On WhatsApp, on Facebook. Okay, we have lots of messages, but all are the non-concerning messages, not from the class. Okay. All right. So this is 2's complement. So let's grab some more notes on that. Okay. We're just taking some more notes on 2's complement. There we go. Okay, one more thing. The most significant bit and the least significant bit. So this is another information that I will going to throw on you. This is also used to remember. This is nothing like out of the world thing. That's pretty easy. Whenever we have a set of number like this one we have here, the most left bit is known as the most significant bit. This is what we need to remember. And the most right bit in any number that we have given, the most right bit, the most right number is going to be named as the least significant bit. So this is it's all about. Then this is all conversion. Now, one another practice, why they have mentioned this one as minus 128. Just like I've told you that if I've mentioned that this is a signed bit, this is a signed number, this whole number is a signed number. So as soon as the we have specified it as a signed number, okay, so now you are going to look into this number as a negative number. So if the specified as a signed number, okay, pay attention, listen carefully. If they have mentioned a signed number, and in any number it's start with a zero, the MSB is zero, it's mean that number is a positive number. But in a specified signed number, if any number starts with 1, if MSB is 1, then it's mean that this number is a negative number. So you will going to do what? You will going to convert that number, you're going to treat that number as minus. So let's do one more thing. Let's convert the negative number, the negative number into its decimal equivalent. So far we have converted only positive numbers into binary numbers into decimal, but you need to convert the numbers, minus binary numbers into decimals as well. Oh, where's my stylus? Okay, there I have. Okay, just a minute. A question? Thanks. You're welcome, dear. Okay, so we have a negative number and we need to convert it into its binary equivalent. So that's pretty easy. There are more than one methods of doing that. Oh, just let me, that is 10 11 1101. 10111101. This is the number, and this is a signed number, specified as signed number. So it's mean that it is specified as signed number and is starting with a 1, so it's confirmed that this number is a negative number. So now it is confirmed, so we will going to convert only this set of data. All right, just let me rewrite number again, 10111101. So just we are going to convert this number 1 2 4 8 16 32 64 128. Now this 128 is minus. This 128 is minus because this is a signed number. So MSB, the most significant bit, the MSB, the most significant bit, the most left number, will going to represent as this. This will going to get minus. Okay. So now convert the number. Let's convert the whole thing. Okay, convert this. What will going to happen? This is 0. All right. This is 32 plus this is 16 plus 8 plus 4 and plus 1, and definitely we have this number here as well, that is minus 128. So add up these all numbers. 32 plus 16 is 48. 48 plus 8 is 56, and 60 and 61. So what we need to do, definitely add up this 1 minus 28 with 32 as well, this whole number, or you can say that do this minus 128 plus 61. What will be the answer? What will be the answer? Calculator, please. My bad, my mathematics is really not good. And also need to be confirmed. So, or you can say another way around, 128 minus, oh, do it like this, minus 128 plus 61 minus 67, right? So minus 67 is the answer. Let's check it. Minus 67 is the answer. So just like this, okay? So that's pretty easy. If they have given you one number and they've mentioned that that is specified as a signed bit, just look into it. This will going to treat as, it doesn't matter that how much long that number is. It could be like only the number could be like this, 111101. So if this would be the number, what will happen then? And it is specified as signed, so this will become minus 32, and you have followed the same thing. And if they have specified it as a signed number, okay, and you have this number, nothing happens, because the MSB, in that case, MSB is what, 64. So you're going to take it as positive, not the negative then, okay? So just remember that. So method of converting a negative binary number into binary 2's complement, we have done it already. That's pretty enough. So there are one or two methods, but the method that we have done is enough. Exercises: convert the following 2's complement number into binary. They have mentioned that this is a 2's complement number, or it's a signed number. So the most MSB is 0, so it's a positive number. So the answer will be, let me guess quickly, 1, 2, 4, 8, 16. 16 and 8, 24. 4 is skipped. 26, 27. 27 should be the number. So 27 is the number. It's positive. Okay. So now they have given this one another number. MSB is 1. So it's a negative number. 1, 2, 4, 8, 16, 32, 64. Minus 128. So minus 128, you have to add all these numbers. You have to subtract these all numbers from minus 128. So it is 1, 2, 4, 8, 16, 32, and 64. So it will go into all our ones. So it's going to make, I guess, 127. 128 minus 129 should be 1. Just let me check. Minus 1. The answer is minus 1. Okay. So this is how it will go, because of simply minus 128 and plus 127 is going to give you minus 1. So on. So it's pretty easy. Just do with all the exercise here. Solve the questions first, and then expand them and check them that if you're right or not. Let me know. So we are all done with all the number system conversions, and we are done with the 2's complement as well here. So hasta la vista. Let's say bye bye, and do let me know on the Facebook. Do let me know on the WhatsApp if you're facing any problem. Just do let me know that if you have liked my lecture or not. So honestly, give me a critical review. Thank you so much. Thank you for being with us. Bye bye.